I have the pleasure today of introducing Sarah Davidson. Sarah Davidson is a senior geoscientist with diverse research and industry experience in fluvial geomorphology, and she also leads BGC's surface water team. Before telling you a little bit more about Sarah, I wanted to lay the foundation or the context for this particular project. So Pat Grover, who is just on the call now, and another one of our colleagues as part of the Cambio team, a few years ago, they started really pushing for us to host a hackathon. And it's a concept that comes from the software world of bringing teams together for a condensed weekend or a few days to be able to really focus on pushing forward on a project. And so 5 years ago now, we hosted our first ever hackathon. And the project we're going to hear about here, RiverBank AI, was one of our hackathon projects. It was actually the winning hackathon from the 2024 hackathon. So pretty exciting to see that initiative and then the development that's happened on this project since that time. Bringing it back to Sarah, her expertise focuses primarily on the influence of floods on river morphology, with a specific emphasis on mapping and modeling climate change. She's also developed a bank erosion model that has been applied to predict riverbank erosion in a range of street types worldwide. She remains closely involved in state-of-the-art research through her role as an adjunct professor at the University of British Columbia and through research work like she's going to present today. So over to you, Sarah. Looking forward to hearing about it.
Thank you, Lauren. That's a great place to start with the hackathon, because I should acknowledge that while I have myself on here as the presenter, this is really a team effort. And my other team members are Kaio Stringari, who is still on the call and will be answering any technical questions that come up, and also presented a little earlier today on other work that he's done. Stephen Brazda, who's actually traipsing around in the field today, so he is not with us on the call, and Lucy McKenzie, who is on parental leave, so handling a 3-month-old. So I'm going to walk you through somewhat of a high-level discussion of what we've been doing for developing this tool called RiverBank AI since the hackathon that happened back in March. I'm going to keep it somewhat high level because that's the level at which I understand it. And the real brains behind the actual model development has been Kaio. So our objective here is to develop a tool that will allow us someone's got their mic on.
Sorry.
I think. So it's to develop a tool that will allow us to detect and also monitor morphologic change in rivers more effectively. And I'll go through some of the existing tools that we have and where we think this fits in. But first, I just want to touch on what I mean when I say morphologic change. So it's really any change in river position or form due to hydrotechnical processes. And it can occur really suddenly during a single flood event. So I'll show some examples of really drastic change that happened, some of them from 2021 in BC. And how severe a flood is and how much widening occurs depends on both the forcing, so either how much rain there is, how much snow melt, or worst of all, kind of a combination of the two, rain on snow. But it also depends on watershed factors. So how much sediment is there? How large is that sediment? Do we have intact forests that are able to evapotranspire away some of the flow and give us bank strength? Or do we have dead wood that's in the river and possibly enhancing the morphologic impact? And then also wildfire is a major kind of accelerator of morphologic change because you have a loss of bank strength and also some loss of that attenuation of peak flows too. What does morphologic change look like? So these are two examples from the 2021 flood in BC. The top one is showing bank erosion. So this is an area on the Coquihalla River where the river eroded its banks. So it moved laterally and affected the Coquihalla Highway and also a pipeline that we can see exposed in the river there. And the second example here is an avulsion. And an avulsion is when the river actually kind of jumps to a new location in the floodplain. So this example is from Merritt, where the Coldwater River avulsed down Pine Street. And so what we want to do better is be able to both understand where these changes have happened in the past, because that can tell us about where changes are likely to happen in the future, but also be able to detect these kinds of changes really quickly after an event without necessarily having to send people out, especially in remote areas. Because as we can see, these obviously can have a huge impact on both people who live in communities, people who use these roadways, and infrastructure as well. So I'll start with how we've done this in the past. So we've done hundreds, if not thousands, of assessments of rivers in the past using a manual approach. And so using this manual approach, what we would typically do is delineate the bank lines before an event in a GIS system. We would then map the bank lines after an event, and then we would compare them to see how much change had occurred. And we'll often do this for a number of sets of previous air photos and satellite images to get a sense of how a river has changed over time. This is an example from the Nicola River, also from the 2021 event, where it pretty much doubled in size. Another approach that probably you've heard about in this symposium in the past is a morphological change detection tool that's been developed by Janine and others. And this is a really great tool for comparing different periods of time and looking at how the river has changed over the long term or even over shorter periods of time, like just a matter of years. And what it does is it takes a lot of satellite imagery and maps water occurrence and looks at what the percentage of time is that different areas are inundated. And then it does that for a recent period as well. So in this case, it was looking at 1985 to 2012, and then looking at 2013 to 2023. And then considers how does the water occurrence change. So it's not actually mapping the bank lines, but it's mapping the inundation extents. And if an area becomes persistently inundated that wasn't before, then that's indicative of erosion having happened. And so in this example here, we can see if we know what areas have been inundated in the past, and then we compare an even newer, more recent period after a flood, we can see where there's new persistent inundation areas that weren't previously inundated. And this is just showing the example of mapping that was done for the Skeena River using the morphological change detection tool. So these approaches are great, but they have their limitations, just like any approach does. So manual digitization is obviously a very big pain in the butt. I spent the first several years of my time at BGC doing hundreds of these, and it is very time consuming. For morphologic change detection, the tool works really well for large rivers and can use fairly low resolution imagery, but because it's looking at periods of time, it is beneficial if it's kind of comparing two periods to each other rather than looking at changes from one single image or event. And also because of the resolution that's often used, it's more applicable to wider rivers. And so our idea with RiverBank AI is really how can we leverage computer vision models and high resolution imagery to be able to both save ourselves the effort of that manual digitization, but also to move towards more real time or close to real time observations of changes and alerting. So as Lauren mentioned, this idea was born for the hackathon last year, which I think was either February or March 2024. And so, yeah, we wanted to know, how do we combine all this work we've done manually with computer vision models that can do image segmentation and come out with automated river delineation that's actually delineating the river bank and bars rather than the water occurrence. So this is showing the work that was done during that hackathon in March. So we came up with version 1, or rather Kaio did, while the rest of us made ourselves useful doing training data sets and making presentations. And this just shows that we give it an RGB raster with a training mask where we've actually identified in that training data set what is river bar, what is inundated river area, and what is floodplain. And then the model comes out with a prediction of what in the image is riverbank and river bar. And in this case, it's applied to the same image that was used in the training data set. So after our original hackathon project, we got funding from Enbridge for this year to work on improving the model and applying it to some of their sites, which I'm not going to discuss their sites here, but wanted to acknowledge them for that funding that they've provided. And so we kind of got to work with figuring out how can we improve the model. And so this example on the left is an example of a performance metric. And essentially, these performance metrics are looking at how well does the predicted bar area and water area match what we said it was in the mask. And this has been pointed out already by John Danielson and also by Kaio, but really we're training it to do the same thing that we did. So often when we look at it, it's actually kind of subjective to what you define as riverbank or river bar. There's often trees overhanging. And so there are times where the model is calling something riverbank or river bar, and we look at it and say, oh, actually, I could agree with that, but that's not how we did it. So yeah, we are forcing it to try to make the same decisions that we do, essentially, our own flawed human decisions. So we looked at about 20 different potential model architectures and actually came up with a new one that was different from what had been used in the hackathon project. We originally used a UNet architecture and found that the FPN worked better. And so this is just showing kind of the results that we're getting from it now. And so this is a set of test cases that we applied the model to. You can see it's doing a fairly good job, especially in simpler river geometries, like this one here. So there's one area that we had said was water and that the model said was bar, but otherwise it's doing quite a good job. But it's also doing a pretty decent job in some of these more complex river plan forms as well. And just to show you an example of what the original model was doing, this was our first pass at it in the spring for this same site here. So we've seen a lot of model improvements from providing additional training data and also changing the model architecture. So in terms of next steps, there's a lot more work that can be done with improving the model performance. And a lot of that comes down to really giving it more training data to learn from. So this is going to require coordinating with clients and also research partners to leverage what we can of work that's already been done, or in a lot of cases, create new training data sets from imagery that we have. And we'd also like to have it work not just for high resolution satellite imagery, but for air photos as well, which are often black and white. We want to actually start applying this more in ongoing project work. And that's mainly going to be in terms of saving that effort of manual digitization to start. And then lastly, moving into really the ultimate goal for this is developing a workflow for incorporating this into erosion alerting. So we have flood alerts that we get when a flood has occurred. We have flood forecasting alerts in some cases, or are moving towards that. But it would be really great after an event has happened to be able to quickly identify whether there was erosion, whether the bank line locations have changed, without having to send anyone to site right away, or to help with prioritizing where people should go after an event. And this is going to require a workflow for tasking satellites, for example, after events and comparing pre and post flood conditions. So with that, I will leave you with contact details, but again, just wanted to emphasize that this was by no means just me. Got 3 other teammates here who you can definitely reach out to as well.
Thanks so much to you, Sarah, for presenting on behalf of the team, and also thanks to Kaio, Lucy, and Stephen Brazda. I think I saw quickly someone raised their hand, so feel free to speak up if you've got a particular question. It looks like Kaio is also joining to be able to answer questions, unless you wanted to ask one there, Kaio.
No, I'm just here to answer any questions and technical questions if there are any.
Sure. That's great. Well, I'll keep monitoring the Q&A and the chat, but a question that I have for both of you is, this idea was born at the hackathon this year, and I'm curious if you were to say what the next iteration should be at the upcoming iteration of the hackathon, what do you think they should do next? Or your team should do next, whomever picks it up?
Yeah, to me, the main priority is really making this applicable. So figuring out how is it that we actually use it to help inform decisions. So saving time is amazing, but I think that we also want to leverage this as a way to, like I said a few times, prioritize where to put our attention after a big event, or understand what's happened in more remote areas where we maybe haven't done past assessments. I don't know if you have a more technical response to where to go next with this though, Kaya.
Yeah, more on the technical side, like, I mean, the models that we currently have trained are from 2012, maybe. So bringing it to the latest and greatest computer vision models would be the next step. Also, probably leverage more of the data that we currently have at BGC, because we have thousands and thousands of manually digitized bank lines. We need to find a way to use that data that's already digitized to further train those models, because we did have still a small number of sites that we trained on. So if we manage to easily and quickly leverage all the data we currently have, we could make a much better, much larger model.
That's great. I see we've got a question from Victor in the chat that says, can you maybe include Landsat images that detect water with NDWI with Google Earth Engine to check before and after events?
Yeah, for sure. We can do that with the more computer vision models, but this is also what the morphological change detection algorithm already does. So the morphological change detection algorithm is based on not NDWI, one of the variations of NDWI, but that's what we currently do with the morphological change detection model. In the future, yes, we will probably start including satellite data into the RiverBank AI model as well. Not only Landsat images, but probably like Sentinel, Worldview, and whatever you can scrape from the internet.
Yeah, and what leads to a certain preference between the satellite images that you're looking for?
I think resolution would be a good like parameter. With the current models, we already see that like the lower resolution data sets are harder to train, because sometimes a tree looks like water and you only have one pixel to decide if is this a tree or is this water. So probably Landsat is too low resolution for this application, I'd say. But things like Worldview and Spot, probably we should start integrating those soon.
I would just add too that the lower the resolution the imagery, the bigger the river has to be for it to be useful.
Yeah, that's a great point, Sarah. I think that brings us to the end of our time for RiverBank AI. So again, thank you to Sarah and thank you to Kaya for helping to answer questions. We're going to pass it to Saman to introduce our next presentation.